Good morning, friends. We had seen problem on design of two-way slab. Now we'll see second problem on design of two-way slab. So here is a problem number 2. Design a two-way slab for panel of effective size 5.6 into 4 meter. See here again, effective size is given, that is effective length is given, that is 5.6 is Ly and Lx is 4 meter. You have to use 4 meter as a shorter span. Simply supported on all four sides. It carries a level load of 3.5 kN per meter square and a floor finish of 1 kN per meter square. Use M20 concrete, Fe 500 steel, body finish factor 1.2, 10 mm diameter bars and effective core of 20 mm. Take alpha x 0.099 and alpha y 0.051. Do not apply check for shear and bond. Draw the cross section along shorter span. This is the problem. Here the steel grade is given as Fe 500, that is Fy 500 Newton per mm square. Concrete grade M20, that is MCK. FCK is 20 Newton per mm square. Then modification factor 1.2. You have to use 10 mm diameter bars. Alpha x alpha is given. Ly 5.6 meter, Lx 4 meter is given, and we have to design a two-way slab. This is the given data, just I had recalled it. That is Lx 4 meter, Ly 5.6 meter, live load is given, diameter along x direction is given, modification factor is 1.2 given, cover 20 mm, alpha x alpha y values are given, fck fy these values are given. So first step is estimation of slab thickness, or to calculate the effective depth of the slab which is assumed. So as Lx is 4 meter, which is greater than 3.5 meter, and live load 3 kN per meter square, which is greater than 3 kN per meter, and Fe 500 is used. So D is equal to span upon 20 into MF. That is, this D assumed is 166.66 mm. You can say it as 170 mm. Then overall depth considering the cover and diameter of bar, or you can consider the directly effective cover as 25 mm or 30 mm. You can calculate the overall depth. That overall depth is 191.66. So provide D 200 mm. Its first design is effective depth 166.66 and overall depth 200 mm. So effective depth can be calculated by considering the overall depth as 200 minus 20 minus 10 by 2, that is diameter by 2, that is 175 mm. That is overall depth 200 mm and effective depth is 175 mm. So you can go through any way to calculate the overall depth and effective depth, no problem. Then effective span, Lx, that is shorter span, is given as 4000 mm plus 175, that is effective depth, that gives 4.175 meter. Ly 5600 plus effective depth, that gives 5.77 meter. Then load calculation, dead load of slab is 25 kN per meter cube, that is 25 is the unit weight of slab into 1 meter width, 1 meter length, and 0.2 is the overall depth, that is 200 mm is the overall depth, that is it gives 5 kN per meter. Then live load of slab is 3.5 kN per meter, floor finish 1 kN per meter. The total load is addition of this dead load, live load and floor finish, that is 9.5 kN per meter. So factored load 1.5 into this total load, that is 9.5, and that factored load comes to be 14.25 kN meter. Now BM calculation, that is bending moment along x direction and bending moment along y direction. See the formula, alpha x into factored load into Lx square, that is alpha x 0.099, working load, that is factored load 14.25 into 4.175 square. It comes 12.667 kilonewton meter. So you have to calculate the bending moment along y direction. It is always less than the bending moment along x direction. So I have calculated directly the bending moment along x direction, not along y direction. But it is required while calculating the steel area. So to calculate the effective depth of slab required, equating mu limiting is equal to mu x, that is 0.133. Since the steel grade is Fe500, for Fe500 the mu limiting value is 0.133 FCK BD square, that is, and bending moment is 24.590 into 10 raised to 6. So by calculating all these values, the value of D required is 96.14 mm, which is less than D assumed. So provide 175 mm the effective depth. Then calculation of steel. Same steps as adopted in one-way slab or cantilever slab. Put all the values here. FCK, Fy, moment along X, FCK, B, D, and calculate the main steel along X direction. It comes to be 339.66 mm square. Then spacing for this along X direction, that is Sx, same formula, B into area of one steel bar divided by total AST. It comes to be 231.22 mm, and it should be minimum of 3D or 300 mm, whichever is less. So providing 231.22 mm, say 230 mm center to center. So provide 10 mm diameter bars at 230 mm center to center in X direction. Now area and spacing of steel along Y direction. So calculate the D dash. Here D dash is D minus diameter of bar along X direction, that is 175 minus 10, that is 165. So put here D as a D dash, that is 165 mm. Here D dash 165 mm, and take the moment along Y direction and calculate steel along Y direction. It comes to be 181.56 mm square, but minimum steel required is 210 mm square. So provide minimum steel as 210 mm square. Then spacing of steel along Y direction, use same formula, spacing of along Y direction, width into area of one steel bar and divide by total AST along Y direction, that is minimum steel area, that is 210. That spacing comes to be 239.35 mm, and minimum should be 3D dash or 300 mm, and minimum is 230 mm, say 230 mm. So provide spacing along Y direction as 230 mm. So provide 8 mm diameter bars along 230 mm center to center. Thank you.